Hi, my name is Bob Greenyer and I'm a volunteer with the Martin Fleischmann Memorial Project. So welcome this 28th of September 2025 to O-Day Intersection. How is everyone out there in YouTube lands? Thank you for joining us, Ken Pratt, Todd Hall, Benaneta, Mika Avila, wonderful to have you, Simeon Hine, Brandon B. Athena Mack, and of course, Gordon Doherty, an artifact. It is very good and fills my heart with joy to know that you have safely returned to your homeland. Hi, Daz Pizzazz and Gary Johnson. So we have a quorum in the house. And today we also have some special guests also lurking in the background. One off camera and two on camera. Who do you think they are? Who do you think they are? Hi, Vanilla Isis and Nathan for DIY Projects with Troutsis. We have people representing from Australia. That's good. Omega, great to have you here. So who do you think we got in the background? Hi, Melons Boy and Green Hiker. Who have we got in the background? Any guesses? Well, maybe you can guess if they say hello and hello. Guys?
Hello.
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 One might be easier than the others. Well, that's the mystery guest who's not on camera. Can anyone tell who we have? Hello, Nick Knock. Right. Yin Gazda apparently has joined from the Czech Republic. That might be a clue, guys. That might be a clue. We have one Paul Harris. Yay! And one Roger Green joining us with Yin Gazda over to the side, commenting, it would seem. Now I know why she wanted the office password. Okay, well, tonight we are going to be talking about O-Day Intersection. You might be wondering why I have named this intersection, and that is probably true of everyone in this room, because they don't know why I've called it intersection. But what we're going to talk about is an experiment that was conducted at the recent Advanced Energy Systems here in the Czech Republic, specifically in Prague. That is the 25th year edition of this Advanced Energy Systems. And I had the pleasure of working with Ava and Roger, who did fantastic organisation, as would be attested by anyone that attended it. And also with actual interaction with Yanrak and, of course, Paul Harris. Yeah, so this was one experiment for those that have an old version of the book of Matsumoto here. If you go towards the back, we're talking around about the 250s pages. The description of the one that we were trying to achieve, I think was on, where I will tell you, it is on page 240 here, and it is S71, and I shared an image of a video actually previously of his actual recording of his S71 experiment. And the idea is that we have potassium hydroxide, 1.5 molar solution, and we attempt a shot. That is to say, an application of AC. He used 60 hertz at 120 volts of 800 milliseconds. But in our case, of course, we didn't have 60 hertz. What did we have, Paul?
50 hertz here in the...
Yeah, and we used a variac, didn't we? We set the variac to?
120 volts.
120 volts. So we had 120 volts on the variac, and the only difference is we had a few cycles less per second. And when we look at this, we did 800 milliseconds. Now, one of the experiments, I shared a video earlier today of 3 of the experiments that we did in a row. In fact, 4 if you include the one in the jam jar. And what we did was we had, I think one of them may have been around 800 milliseconds, but the one that we're going to really study was the last one where we had the slow motion there. And that was about 250 milliseconds. So we weren't even firing up to as great a degree as Matsumoto. But what I will say is, at least from the S71 experiment we shared, we got a little bit more sparky action. And one of the researchers who have attempted this is Nikita Vivok, and another one is a guy who joined us very late in the proceedings. He says, "Can I bring a high-speed Cronus camera and come to and record the action?" And I said, "Absolutely, you can." So he found an affordable flight and came over and joined us. And if you just bear with me a second, I'll find his name. And I'll let Paul and Roger talk about some of their experiences while I do that.
Yeah, hey everybody. Yeah, it was an excellent turnout. We had a wonderful time. We started off with the older Alchemy of Prague with working with mushrooms, and we did a field day and found quite a few different species that were very interesting. We ate some of them as well, and that was great. Made some tinctures with the spagyric process like Matsumoto, and then began the advanced day at Jan Rak's lab. Well, actually, we started on the first day. We just did the lecture series in Prague, and we each did a presentation that went really well. And Jan gave a great summary of his history and some of his ideas and understandings of where this is all going, and implementing the idea of consciousness and unifying science and spirit, so to speak, in some of his new things that he wants to work on with the lab there. So that was great. And the lab was spectacular. Of course, his whole team is excellent builders, and their equipment was top-notch, and we really had a great time.
Yeah, it was certainly a fun time. So,
I'll say a few words.
Oh, for sure, go for it.
Hi, Bob's World. Roger Green here. This is about the 7th Alchemy of Prague event we've done, and it evolves as the world evolves. The theme is always ancient alchemy to future alchemy. So we start off with the old-fashioned alchemy. We do that in the Edward Kelly John Dee Tower in Prague, which is probably the most historical place to be doing old-fashioned alchemy. And Paul sets up an old-fashioned alchemy lab, and we've been doing plant medicines, spagyrics and tinctures, but this year was very, very special. Paul, for the first time in a way, we did a lot of work with the fungi kingdom, and historically there was never much reference, there was virtually no reference to using the fungi kingdom in the alchemical experiments of the past. So Paul did a brilliant job, also bringing the fungi alive with a synthesizer and playing it into several fungi, and we sort of had a fungi orchestra for the first night. And then we had it sort of evolves into what we call the advanced energy systems, and there was a selection of experiments from cold fusion to Matsumoto's work, and we had a global group, people from all over the world with very, very high energy.
Hawaii, Australia.
Yeah, people flying in from two sides of the Pacific.
Right.
Hawaii and Australia, the Central Pacific. We had people from the West Coast, East Coast, lots of people from Europe. It's really good.
There's a little review. I just put together a little review.
Yeah.
You can probably find it on my YouTube channel. I mean, if you were to kind of go into YouTube and go Roger Green, Alchemy of Prague, it should come up as this. You kind of get the overview of what we did in the last week.
I'll drop it into the blog afterwards, so
Yeah.
people can see it directly. So, yes, the person I'm referring to is Andre Green, so thank you for the fill there, guys.
Yeah.
And, sorry, Andre Romero, rather, not Roger Green. I was mishmashing words there. So
Andre came from Salt Lake City.
Yeah, Salt Lake City. And, so a huge thank you to Andre Romero for his huge contribution there. And before I go into that analysis of that, I want to show you another piece of work. I'm going to talk about this more when I've had a chance to study this under the SEM, and so I will give credit when that comes. I haven't got permission to say his name publicly, so I'm just going to show you the images right now because I think it's relevant to what you're going to see on these spots that were created in the experiment, the replication of the S71 experiment. So what it is actually a lightning strike that occurred in America before I traveled to America in August, and you can see here on the telegraph pole, so I think we've got power and communications going on this pole by the looks of it. There was a lightning strike that came down the lightning conductor, and it did some quite funky things. There's a track over here and there's a track around here which kind of comes out of the tail of this side here, but this one is not joined. And when you look at so we're going to look at this one down in the bottom left hand of this portrait photo. You can see it's shaped like this, and it's kind of not connected to that. And then we have this other, this is a close-up. Now, I actually have the slug out of the ground here with the copper grounding wire went into the ground. And so we're going to be able to study that in some detail in the future. So I'm very excited to look at that. And you can see here the copper oxide, this red kind of merged, fused into the ground, and the way it's burned. And also the fact that it's taken out this chunk of the wood from the bottom of the telegraph pole. So very excited to look at that. But here, when we start to look at what's on the paving slabs, we're starting to see this kind of dendritic kind of tendril coming across here, and it's this very sharp bend going on here. Now, this wasn't immediately after the event, so there may have been some foot movement over the top of this which may have damaged these structures, but we can look into them closer in both of the sections. And here we start to see how they've got a line and a bit kink, and then a line and a kink, and so forth. Thank you, Vanilla Isis, for that $30. That's really, really appreciated. And here goes a little bit look of one of the sections as it goes across the gap in the concrete pads there. And then we're going to go and look in a lot closer. And when I look at this, I see, for those people that have seen the videos and images that I've shared of Jan Rack's Dragon Arc discharge, it's not too dissimilar, actually. And you'll see here that we basically have a zig with a bit coming off, a zag with a bit coming off, and I imagine it's coming from this side. So we've got it coming up here, and then we've got a bit coming off, and then it kinks off to one side, and we've got a bit coming off, and then it kinks over this side, and we've got a bit coming off there, and a bit coming off there, and it kinks off there. This is the kind of thing that you see on the Dragon Arc discharge. The difference here is that there's this little impression in here, which I find very fascinating, because as far as I can work it out, this is actually the footprint of the former copper conductor of the lightning conductor from the top of the pole. So you can see it spans all the way along here, all the way along here. You can see what would likely be copper oxide here. Now, here we are looking in even closer, and you can see these kind of structures here look very similar to the kind of structures of ball lightning in the Vega Valley as it's traveling from the valley and out through the two brass sheets. These kind of like churned up glassy structures. This is very glassy, and you've got to imagine that it's taken out some of the silicates in the aggregate mix of the concrete here and fluidized it and swirled it up. But also, where has the copper gone? I mean, where has the copper gone? It looks like it sank halfway in. Now, was that because it was so hot that it caused the concrete to, melt and it fell halfway in? Or was it actually that there were so many charge clusters in that piece of metal that it caused, a churning of the material in the same way that we see in, for instance, the Neil Crichton Gold line reactor, or in some of the work of Ken Shoulders, where it's actually boring through material that is refractory ceramics, like fused quartz or alumina. And you can imagine that many of those same kind of chemical compounds are making up the matrix of the aggregate and the concrete here. So I actually have been given samples of these incrustations by the person. So thank you to him. I will verify in the post where I focus on this after I've done an analysis whether I can give his name out. But again, here you can see these kinks and bends, very Dragon Arc discharge-like, but in like a 2D plane version of it rather than a 3D structure. And here again, now you're going to see something on the SEM imagery of the exposed copper plate to the S71 lead wire experiment that also reminds me of these kind of structures. So if I just go back to the original images up here, it is this gap here, like there's nothing here. And I wonder if the copper that blasted out from here hit down here, and what you're seeing is the energy solitons, the charge clusters, coming out and moving the copper, and possibly some of the black here is not just carbon but also copper oxide, because of course copper oxide, depending on which one it is, it's either like red or black. So maybe there's some copper oxide blended in here. So we've got a lot of exciting learning to come from this, and I think this might be the first time that we can look at a strike, or a lightning strike, in the context of energy solitons and exotic vacuum objects. So lots of exciting things to come up there in the future. All right, so I'm going to delve into the data. I'm going to pull up some other images, and I'm going to ask my good friends behind me to fill in for me whilst I do that.
Yeah, that looks great, Bob. It's amazing. Yeah, you can see the black, and I'd imagine that's carbon you're going to see in there. When I first saw it, it looked almost as if the arc had gone under the sidewalk from the grass and maybe came back up through the sidewalk from the bottom. But yeah, I think you're right. Maybe a piece of that copper grounding wire flew over and landed with part of the arc right onto the face of the sidewalk. Because you can see the line. You see the line from the wire there. And the copper embedded right in there.
It's right there, and it's actually a hemisphere cut out of the ground. Yeah. Okay, keep talking, and I'm going to find the imagery for Matsumoto.
If you can imagine that piece of copper flying through the air with the charge still held all around it, and if it had that much force when it hit the ground and that charge dissipated into the concrete and still had the power to vitrify that sidewalk into the glass.
So I just don't think it is heat vitrifying it.
Right.
I think it is charge clusters coming out, because we know that copper oxide stored charge clusters in the Neil Crichton Gold reactor. Right. And it was when he turned the power off and he connected a 30 watt halogen bulb, and he attached it to a sink,
right,
which he never really defined, but I think it's a large lump of metal.
Yeah.
It lit that bulb for 30 minutes.
Right.
And as it did so, there was this crinkling and crackling and sucking of air into the tube, and on the temperature, it went from recorded 850 to minus 273 thereabouts in two sample sections. Yeah. So as the EVOs collapsed and gave up their electrons, they lit the light bulb, but they froze the ground.
Right.
So I think what's going on here is you've got fluidization of the material as it's passing into the aggregate, but then it freezes, so you get glass formed.
Yeah,
it's a two-step process.
Right.
But it's carrying the matter with it as it goes. I think we're going to learn a hell of a lot from this, and. So thank you very much, Todd Hall. We love you too. And Dennis Matovic, we've got 70 people in the house. That's great for such a late showing. Young Say, a new person. And thank you, Stone, another young new person here. So thank you for joining us, Omega and Finn Bear. Wonderful. Right, okay, so keep talking, Paul, and I'm nearly there.
And there was that one paper that I referenced in my talk on the day before the lab day. And it was about exploding wire experiments, and they had shown that the amount of energy that they're putting into the wire, and they just take a thin wire and a large capacitor and basically dump megajoule of power into this little thin wire, how the power that was dissipated and measured through the heat and the mass, the amount of energy that would be in that mass, there was a higher amount of energy that was dissipated than what was in that mass, and if you calculate out the amount of a charge that was put into it too. So that's interesting, right?
Yeah, it's really, really interesting. Okay, so what is also very interesting is this. This is the impact zone that you saw in the experiment. For those who actually looked at the experiment earlier today, did anyone look at the experiment? If not, here is the experiment here, or one of a similar kind. This is recorded at 4,000 frames per second at 800 by 600.
That's 100.
Beautiful.
There you go. Look at that.
Wow.
So actually this is 250 milliseconds, and as you know, in every 0.02 of a second, that is 20 milliseconds, you're getting a cycle from 50 hertz. So it goes through a number of cycles, and I think you can almost count them. And we go all the way on to the end here when it's all settled down. But if you look at this first one here,
Right.
if we go through it here,
So
one cycle, half cycle, two
two.
cycle, half cycle, three cycle, half cycle, four cycle, half cycle, and then five cycle, and then I think the sixth cycle or whatever. It's something like 4 to 6 cycles going on in there. And the last one blows everything out of you, and that's where I guess you get twitchy fingers there, Paul, and switch it off.
Yes.
But you can see it more real time on the video that I shared earlier today. And if I go to that, there's several ones that I showed. This is the overall experiment that we did. And so this is Paul and Jan. Paul in the center of the frame. So the guy doing all the calculations for the molar is Andre Romero over here on the right. So thank you to Andre Romero. So just let you know, what did you Andrew use for calculating the molar solution?
Oh, we just used grok and said, okay,
Oh, there you go.
if we had 6 grams of potassium hydroxide, how many milliliters of water would it take to make a 1.5 mole solution? And boom, gave us the answer like that.
So the first one you did, which was the trial to be.
So we've mixed up our.
So he talks about the, and you can go and look at this. So I actually, this is one of the few experiments I got a chance, because we only had the SEM for a short period of time and we're also running experiments. But this was the only one that I had a chance to look at some of the material before we started. And the copper and oxygen here is the majority of the weight of the material. In fact, accounts for 97.7% of the mass of the material. And there was some carbon content on there, 10.42%, and by weight is 2.3%. Now, actually, Andre Romero did in fact note in his experiments replicating this experiment that if you had 0 carbon in there, you tended not to get any sparks. And it's interesting because in Matsumoto's own experiment, you don't really see any sparks. But of course, he saw transmutation going on, and the principal transmutation was to carbon. So that is the facts as are. And I think because we know we had some carbon here in the copper, we can't say we didn't have any carbon in there. And we didn't get a chance, but we do have a sample of the lead, and we will post-experiment verify the lead. But this was an initial sort of introduction to replicating this experiment to see if you got the broad spectrum of observations in the structure that gets formed. And so here we do one experiment here, so you can see Paul getting down there, and we'll just show you he's getting in there, and the guy's getting there afterwards. So when do you do it here?
Okay, run a couple. All right. Yeah, this.
Yeah, okay, so he does one here.
4,
Okay, here we go. Countdown.
2, 1.
That's it.
There you go.
It's just a little flash. That one wasn't recorded, but it was just the test run. And then that is what the electrode looked like on the second run, and we're going to look at this electrode in detail in SEM. And then, in fact, then we did one with the high-speed camera with the lens that Andre brought with him, with a light that I brought.
Yeah.
And it's very important when you find lights to illuminate for high-speed photography that you have a light that is able to be dimmed, or whether it's dimmed or not, it is not flickering at all. It needs to be an LED that's on at 100%, or an LED that's synced to the camera.
Right.
Now the LEDs that you can get to sync to the Cronus cameras are fantastically expensive, but they are very bright. However, it's probably better and much cheaper to get, at least for those that don't have unlimited money, to get these kind of lights. And I will try and share in the blog which kind of light works. But I made this mistake when I did my initial high-speed photography in ultra experiments. I used lights, and there was all kind of strobing effects going on that messed up the video recording, and that caused bands to travel across the sample. Anyway, I identified that this is good, and Andre did the first section, which you'll see here in a second. Okay. Did we do it? There we go.
All right, so I just have to be that close.
Okay.
All right.
So you guys are standing there. All right. Let me shift the next one over.
I don't know how much.
Okay. I'll prepare
You have
this.
to focus through that crack.
Yeah, it's going to be difficult.
Okay, so what we did is we set it up differently so that we didn't have a cover over the Petri dish.
The first one we were concerned about it splattering too far up,
Yeah.
so we had a bit of a Petri dish lid over it. And the second one we determined we didn't need it. We got that jar out of the way though, which is good.
Okay.
And when we show this, you'll see down in the bottom right of the frame that I show the high-speed photography. And just note that the video that I've uploaded, which is in the blog, is actually this whole frame is in 4K, and the frame down in the bottom right of the high-speed is in actually its native resolution at full resolution. In this YouTube stream, it will, and it's all at 30 frames a second, both of them. Whereas in this stream, it'll be at 1920 by 1080 and at 25 frames a second. So the better quality image, if you want to step through this and study it in detail, will be in the video I uploaded.
Yeah,
earlier.
get focused.
Right.
Yeah, go ahead. It's on.
You ready?
On now.
Okay. 5, 4, 3, 2, 1. Yeah, we might need to be a bit closer. Okay.
No, it's not working.
What did it not?
The breaker.
The breaker did go. Okay. That's all right. Yeah.
So the breaker had gone on
So-
previous experiment, so we have to go and trip that.
Yeah, and that was part of the problem with our timing. We couldn't exactly time that arc because it depended on how long it took for the breaker to trip.
Yeah.
So there were.
And of course, we had to time up the high-speed camera and stuff. So anyway,
Okay. Ready?
There we
5,
go.
4, 3, 2, 1. Ah, nice.
That one was longer. Yeah.
Yeah, okay, that's why I put the lid on there, but stand back.
So anyone trying this at home,
Okay.
make sure you
No, that's
have
done.
good ventilation.
It's done. Yeah.
Steer clear of that vapor.
That's it.
so yeah, you could see down here it's chucking out a white fume and lead oxide. At least one of it is white.
Right.
So you probably don't want to be having a good lungful of that. You actually can see it coming up to me, but I took one for the team. I would suggest that if you're playing with this at home, get yourself a good fume cupboard, or have a good vacuum cleaner
extractor.
above the experiment on a good old suck when
Yeah.
you run the experiment. So
Yeah.
that's what I would recommend. And then what we did later on is we set it up differently. So we had 2 lights on it, and I had, fortunately, a bunch of different lenses. So this one over on the right is with a Sony mount, and then I had another one with a Canon mount, which fitted the adapter that Andre had brought with him. And unfortunately, it's not a powered lens, and so I had to switch it back into my camera and get it into focus at a short distance. and then handing back the lens where the focal plane was more optimal for the experiment. So you can see Andre now has got it in place. So thank you again, Andre. And by this time, I've now got 2 lights on the situation, and Andre thinks he can play with very high frame rates, but extremely small exposure time. So he does 40 microseconds, I think, exposure time. It does leave it a little bit dark. And of course, this is where the experience comes in. You want to get a good combination of spatial resolution, number of frames per second, but also your exposure time. Now, what is the relevant point here? Well, if you have a very short exposure time, what that means is if I've got like a blob and it's going through free space here, I'm not going to get a blur, right? I'm going to get on my 1/4000th of a second frame, I'm going to get it here, and then I'm going to get it here, and then I'm going to get it here. So we don't see a motion blur, we just see the thing in a point in space. If I had to do this again, I would choose a slightly larger exposure time, because then overall it would have been brighter and you'd have still been able to track the key objects. But this is very good in terms of, for what you can see in a particular exposure time, you can see it very clearly, those things that are exposed. So I'll just go back in and play that.
I can both, but
Well, I do want some spatial resolution, so just 720p would be fine. What can you do at 720p?
let's see.
Oh, wow.
Probably. I'll just go to, how about 800 by 600 and
Yeah.
maybe 4000.
And I'd just like to say here at this point that in this room, there are a lot of people that are literally participating in this experiment for the first time. And I think probably this is the first time in the world where a group of people who are interested in the field have been able to come in and participate in and watch up close and personal low energy reactions, a range of different technologies taking place of coherent energy transformations. Now, of course, you don't always get things right when you're doing setups, and we all identify that there's something wrong with this experiment.
Yeah, she's floating in there.
Floating or floating?
Yeah, that's floating.
And it wasn't what Paul is adjusting there, which was the position of the lead wire in the Petri dish. It was something different.
Yeah, it was about 1 millimeter, it's in the solution, but about 1 millimeter above the lead.
Yeah.
But if anybody caught what happened there.
Yeah.
Okay, you ready?
on.
Okay. Let me know when you're ready and I'll count.
Okay. It's recording, so you're good.
3, 2, 1.
You wired it again. I've got
Okay. Let's have a look, because maybe something came undone. Yes.
So my question was, are you wired in here?
Yes, yes, yes. Just make,
To make a second.
yes, yes, yes. You have to plug it in. And you,
That is a single. That is a single
Yes.
wire.
yeah.
You make a circuit, Bob.
He's
Yeah.
just so
I'm just so used to Tesla.
used to test.
Yeah, there we go. 2 wires? Who would ever use 2 wires? Okay, ready? Let me know. 3, 2, 1.
That works.
That's a popper.
So you can see down here in the bottom right, this is the 250 millisecond one. And you can see it's just a number of cycles that go on before you get this beautiful explosion. And that is it. That is the experiment, which we're all getting very excited about here. So there we go.
You also saw in the front of the frame there, the other camera that Steve brought from Australia was a full spectrum camera, so it saw the UV and the infrared as well. So there
Yeah,
should be
so
some-
we'll be able to share that at some point
Yeah.
in the near future. I think he's on his way back to Australia, so we'll forgive him for not getting the files uploaded.
Yeah.
But yeah, some more on that to come. But yes, what he'd done is he'd removed the IR and the UV filters. It's an adapted camera to see, as Paul said, the full spectrum. So you see the flash of, I guess, thermal energy and the UV. So you're gonna get to see a little bit different things going on spectrally.
That should be neat.
Anyway, so what we then did is we went and looked at this. I did with SEM. So thanks to Jan Rack for organising the SEM to be there that day, and also thank you to Arnemet in Prague for sending over their director to actually have that SEM there for it to be used that day. And I will hand you over to Paul and Roger, and I will pick up the images.
Yeah, the beautiful, and we got to do 3 or 4 of those runs, and we had to split up the group and take, half the group went for lunch when the other half came back, so we got to do that experiment a couple different times. And the beauty of it all, really, was that Hiroko and her son were there, Matsumoto.
Yeah.
So that was just so special for me to have them actually witness their father's work being replicated in the lab. And of course, all of you out there who've taken on such a great interest in his work, it's just mind-blowing.
Yeah, I second that. It was I sponsored them to come over, and my wife convinced them to come over, and they came over. That's the main thing, and so they were able to participate in this unique event. And interestingly, Hiroko's son, Remo, who was there, he's 27, and this experiment was done in 1996. So actually, he wasn't even born at the time that this experiment was being conducted. Or am I right in saying that? 29. Yeah, he was. He was 2 years not born.
2 years. Yeah.
Or at least a year and a bit not in the belly. And actually, in fact, Hiroko wasn't really familiar with a lot of her father's work. So to see such an important experiment up close and personal, and to watch the whole experiment from kind of like putting it together and running it, and then chucking it under the SEM and seeing the effect, it was a deep honour for me to be able to have facilitated that. And thank you to Roger for organising the conference. And the people that made it possible by actually attending. And really nice thing. So let's have a look at some of the data now. So this is the one of the strike targets here.
Yeah.
And you can see it has this wonderful kind of wavy blob, which is all fractured in the middle. So you can imagine it kind of had this shock wave that went out and it had this melt zone, but also it then kind of like glooped in on itself. The shock wave went out to an area where it wasn't molten, and then because it was not molten, it reflected the shock wave back in and then threw it up, much like a water droplet does in a tank of water when you drop a bit of water in there, and then it froze in place, leaving these cracked areas. Of course, thermal expansion and everything, and the fluid movement you can see might account for these things, but you're going to see a lot more on the SEM in a minute. And it kind of this really looks lead-like. This looks lead metal-like. And interesting, there's these kind of lead spheres with kind of structures around them, and they're obviously traveled. And I wonder if these traveled a little bit like those long-lived plasmoids, but obviously not that long-lived in this case, because it certainly looks like they've swept up an area that would otherwise be cut. So maybe if you look at the original video, you see this kind of film spread out over the copper initially, and then that might have been what made this initial thing on here, the initial deposit. And then these were later structures during the more explosive phase that came across, and then they traveled and swept across. But again, it's got this central melt zone, then it has this zone, then it has this zone, then it has this fuzzy area, then it has this zone, and then it has a kind of boundary layer all the way around the outside, and then a lot more interesting stuff going on the outside. And in fact, all the way out to here.
Another zone.
And this is basically down here in the bottom left here is really the original, essentially pure copper, with a little bit of oxygen and maybe some other contaminants on there. So this is our
striations.
This is our original copper. So this is all action going on from the process, and even there's some odd bits out here which are clearly not the pure copper. And in some places they're really rather colourful and lovely. And this is something you see on another one. So I'll show you another one before we take a closer look at this. This was actually a second macro photograph composite that I did. And in this case, it looks like the strike was slightly off at an angle, or that something formed, maybe a plasmoid, and it travelled across here and kind of died out, petered out with its energy. Maybe this was a tornado, because it's really churned up here with these scalloped kind of sloshing that was described by Ken Shoulders, this sloshing process going on, and then it died over here. But again, in the center of the strike zone, you've got this cracking going on. And so there's lots to learn here, lots to learn. And when you come out here, again, it's got these various zones. You've got this central zone, this area, and then the actual sort of raw copper out here. Anyway, it's when you go and actually look at the SEM, and first, before I do that, I'm going to go into a closer image that I took under the macro photography. And it's take a bit of time because these are very large images. So the wide one was this, where you see a little bit more going on, and you see out to the bare copper. But in this one, you're going to see quite a bit closer in, so we can actually see this sloshed zone with a lot higher fidelity here. You can start to see these more iridescent colors coming in. Over here are these thin film copper oxides. You can also see these cracks are radially coming out. These stress cooling cracks probably coming out radially all the way around. And when we get into the SEM, you're going to see some of these cavities of very special form. And then you can see things that are clearly different thicknesses of deposits on the top. But the reason you have to look with SEM and different imaging technologies is that you get to see very different kind of impressions on the data. So if you just bear with me, I'll hand you back, and Roger might like to talk about potentially next year's up and coming meeting.
Sure. Well, we had an interesting day today. Paul and I were trucking around the outskirts of Brno, which has got some very historical significance with alchemy, and we actually found a spot where we could do the advanced alchemy, which involves the metals. So previously in Prague, we've been working with the plant kingdom and the mineral kingdom, so to speak. Historically, we've done everything from rosemary to cannabis, making these spagyrics, but using the metals, it's a little bit more messier and a lot more smoke involved, so we can't actually do that in the basement of the Edward Kelly John D Tower in Prague. But what we're going to do approximately in a year's time, September is always a good time to come to the Czech Republic. What we're going to do is we're going to do part one in Prague in the basement, where we can do a lot of prep around using the metals. This is advanced alchemy. And then we'll take the group to Chesny Kromlov again, which is this amazing medieval township in South Bohemia. It's just amazing. And previously what we've actually done in Chesny Kromlov is actually we've had a medieval costume party, just for the fun of it.
And a feast.
And costume medieval feast. And then we always visit a glass factory, which is amazing. As you know, the Czechs are just absolutely famous for their glass technology. And then we'll come to Brno and do the outskirts of Brno, this beautiful castle area, right on the head of this dragon energy that comes to the castle. And we looked at the logistics today, and it's just all the ducks lined up. There's a hotel there. We can even do mushroom foraging. There's a water spa. So then we'll come to we'll probably come. I haven't had a chance to discuss it with Bob yet, but we'll come to Brno and do our advanced energy systems again. So it's always a theme of the ancient to the future alchemy, and of course the common ground there is transmutation. And so we'll be talking to Bob a bit more later on about what we're going to get up to with the advanced energy systems in Brno next year.
Yeah.
Any comments on that?
Yeah,
Paul?
so basically what we do in Alchemy is get our sea legs working with the plants in the plant kingdom, and then all the exact same processes that we apply to making medicines in the plant kingdom apply to working with the metal in the mineral kingdom. So we'll be working with higher temperatures, utilizing the same processes, and we'll be able to make very powerful medicines from normally poisonous metals like antimony and lead and all that. We can make some very interesting products from them, including glass-like materials. Speaking of the glass blowing factory, where many of the Gothic cathedrals, the church stained glass windows that were made here as sort of a lost art that nobody knows how to do anymore, but what those glass masters were doing at that time were infusing the glass with these kind of metals and making all the different colors. That's what makes it so powerful when you're standing inside one of those Gothic cathedrals and then having the sun shine in through the window. It's
And we might do
quite an
something
experience.
with gold, do you think, next year?
Yes, yeah, I think we'll do a few things with gold.
If
What
it's
make
even
it
slightly
easier?
affordable.
Yes. Well, we've got some stashed away, so for a rainy day we might be able to pull it out.
Okay, keep going because I'm having a mare trying to get the Mac transferred to this desktop that is actually able to be broadcast. So give me a
Okay,
second.
Great.
I'll be with you shortly.
Yeah, it was spectacular to see the castle. We don't really want to give it away too much, but it is on this set of hills, and those hills have a name for the local area of those hills, and they're actually it is translates directly into the mushroom hills, or the hills of the mushrooms. And we just had a spectacular pre-fall here with a lot of heavy rains that came, so that actually our timing was perfect for the weather. When we got here, it was cool and rainy, and just as the workshop started, it kind of warmed up a bit. And of course, the mushrooms are waiting for that rain to come out and actually fruit. And when we got to the forest, well, there was plenty there. We found quite a few.
And the biggest puffball.
Yes,
that Bob
we
has
actually
ever seen.
found the record puffball that any of us had ever seen. And it literally was like this big. We named him Fred, and he was delicious. We were only able to eat about a quarter of them, and we fed, well, I don't know, several people. Like there was 12 people over. Then we fried them up with garlic and onions. It was excellent.
Okay, so I'm nearly there, and what we're going to look at right now is on the right. Oh dear, it's moved. So what I'm trying to do is I'm trying to run a PC and a Mac currently on the same machine, because the software to view the DZI, which are the deep zoom images, is only available on the PC, and I will make that available for you guys as I have done in the past, so you can go and study and do some metrics on this data. So I'm just going to get everything configured up here, and I think we're nearly there in a second. And pretty much there. Okay, all right. So here we go. So on the left, we see the PC, Windows 11, with the SEM map. And on the right-hand side, we see the optical imaging I took with Sony Alpha. And so you can get some sort of comparison between these two structures here. I had to stop it because we ran out of time on doing the imaging, which was unfortunate, but it's just the way it is sometimes. But you do what you can, and I think we'll get a good proportion of the potential learning out of this. But you can see how these two things are, and the advantage of this piece of software, it's going to run a bit like a dog when I'm running everything together, but we can see the central melt zone quite clearly here, and I can measure that. So I can go across here to here, and we can see that that is about 1 millimeter across, and that's very interesting because that is the size of a basic magnetohydrodynamic EVO from producing the required strength from ion electron plasma. and we can go and have a look again if we do the measurement here across this zone here, across the center there, and that is about 3.16 millimeters. We can go and do the other zone across here, so from this area across to somewhere over here. So we're talking about 5, maybe 5 millimeters across there, roughly. So you're getting a kind of idea of the sort of spatial area. Let's see what the kind of band width is here. And you can do all this in the software with this data that I will be sharing. So this is 730 microns across here, and that's about the size that a quark-gluon plasma would need to be to make the required 10 to the 15 Tesla field. Anyway, we're going to delete all those. I think I can just do it like this. They're going to let me delete them. There we go. That one. Sometimes you grab it like that and then you can delete it. So you can do this, and you can measure angles and so forth. But I remember that we were looking at this lightning earlier. Let's go and have a look at it. Hold this image in your head here, right, as I zoom into this area over here. So does that look similar? I mean, there's no doubt that this is an electric effect, and you saw the sparky going on in the high speed and even ordinary speed imagery. So these are very, very similar things in my view. And what do we see here? We see a sort of lead ball with some structures coming out of the back of it. Okay, we also see a little bit of a ball at the end of this tail. There's a ball up here, there's a ball up here, there's a ball up here with a trail. So if we look here, there's a kind of a little bit of a mark with a trail with 2 sides on it. And this is where you would want to go and zoom in here. But oh my God, what do we see up here? We see a little plume of material coming out of this ball. Now, the reality is, when you are looking at this, the mid-gray here is predominantly copper. The bright white areas that you see, so this mid-gray here is predominantly copper. The bright white areas are lead, and this is the way the EDS sort of imaging works. And the black areas are much lighter elements, that is to say, than copper or lead. And so what are they? Well, we'll just hold that thought, because what you're going to see in here is so many special images. I just want to focus on this area that we just looked at here, and we'll zoom into that, because this is what it looks like in color optics, and this is what it looks like in the DZI. Now the DZI is captured in high dynamic range, so I can actually change the exposure here, like this. And so what I can see, if I move this up so I get my blacks as black, and then I move this down a little bit here, you can see that this area here is all really white, and that is the shiny bit that you're seeing around here. That is a thicker layer of lead. Okay? Then the other thing around here is a thinner layer of lead or lead compounds on top of the copper. Okay? And it's not thick enough in order that there's much of a difference between here. But what you can't really see is these areas, which are actually something else, and I can tell you they are likely to be carbon. Okay? So are the shiny areas over here actually these areas, or are they the thicker lead? And all of this will become clear later when we do a lot more delving in. Now, what is really fascinating to me is when you start to come out, not in this zone here, which is fairly bland with like what looks like basic splatter marks. It's actually this zone out here, because you get these extraordinary array of structures, an absolutely extraordinary array of structures. And they are clearly all lead spheres, or predominantly lead spheres. And as we would expect, often they have a hole on one side. And here, it's spewing out something. Here, this is blown up and then something left here. Okay? All over here, we see these structures. Look at it down here. Look, a hole and a big chunk of something coming out of there. Let's see if we can expose that slightly differently so that it comes out a little bit more. Okay, and we just knock off the highlights there. Okay, and typically you have these kind of crystalline tongues which are thicker with this kind of diffuse matrix around it. You'll see this over and over again. And you also see these little marks. Now what's happened here is the SEM unfortunately was placed on a table that was not very sturdy, and if someone was walking around in the room a lot, it took a couple of samples and it overlaid them. So, but that isn't the case everywhere. There are many cases where it took a frame and none of that problem was occurring. So have a look at this.
Yeah.
Look at that. Now what do you think that is? What do you think that is? I'm in two minds of what's going on here. One, which I'll talk about now, and one which I'll talk about later. I think a ball collided here. It broke up, and its two substructures spat out carbon content within them as it fragmented. And the reality is, when you zoom in, there are quanta that are much smaller that are also spitting out carbon plumes. Mm-hmm. Okay, look at this one here. Now we're starting to see something that this might be the structure that hit here, spat out these two structures, and then died here and left the rest of its payload in a diffuse area over here. So much can be learnt from this. Something collided here, in my view. In this case, there's a helical swirl. Yeah. I think it collided here, and it just spilled its guts over here. This one kind of like maybe started to die above it, and then fell down on the base and left its material here. Some completely destroyed themselves. Now you're going to see some high-res images. Unfortunately, we only got a few, but this experiment is very, very repeatable, and also we have the samples to look at a later time. This is a twisted area here. So what we're kind of looking at in this case are these kind of areas down here, down in this area down here. Yeah. And you're not seeing anything that looks remotely like this. This is why you need to have an SEM. Okay, look at this one. Something died here and spat out these two. And this looks twisted one way and this looks twisted the other. I believe that what you're getting in here is a magnetohydrodynamic structure. When it collides, the two substructures, which I believe are coherent, are spitting out the coherent matter wave, and it collapses. And as you see the more and more data, I think that's going to become very, very clear that this is what's going on. In this case, it spat out the main chunk there, and it's just like, this is one half of the sphere, and this is the other half. And this is, maybe this is a chunk that was on this part here, and it just spat it out. You guys are going to be able to tell a story about each of these impacts. Look, we've got a line over here and a line over here, and then the overall structure has died. It's absolutely fascinating. Many, many structures where it kind of came in and died. Came in and died. Look at this little beauty here.
Oh, that's nice.
Look, it's got actually a trail that comes out of it, out of its pole. This is something that Matsumoto saw. He saw tubes and films. Tubes and films coming out of these structures. And so I don't know for certain whether there was some contamination going on. Look, here we go. Tube and film. Over and over and over again, you see the same pattern. This one like died.
You can almost see inside of that other one.
Yeah. I mean, there are so many here. Yeah. And some of them you can see some sort of helical vorticity going on. We're going to have a look at that in a little bit in a more close-up image. And you can see their breakup products. But yeah, you guys are going to have a lot of thinking to do when you get this. Look at these ones up here. Yeah. Many, many. Impact, spat out, spat out. Impact, spat out, spat out. Impact, spat out, spat out. And I actually wonder whether these aren't the itons that he described from, mistakenly described from his early work. Yeah. You can even see a fragment of the sphere here in the center of this blown up point here. Mm-hmm. Yeah, these are crenellated spheres, but they're crenellated spheres where you are starting with lead. And this is the genius of Matsumoto. The absolute genius. When you look at this, as I said earlier, the lead is white, the copper is grey, and the carbon is black. But here's the thing. When you are crushing something and you're trying to make something else, if you've already got the heavier stable element, which is lead, then where can you go? Well, if you convert that into a coherent matter wave and it gets reborn as other elements, well, there's a good chance it's going to make a lot of lighter elements, because it's the only way it can really go unless you have a very resonant system that's crushing it a lot. Because this is a 1-point cold fusion experiment. It's pulses. It's not resonant. When that explosion occurs, you can see that the things move away and they're not in the same resonant node. The thing about doing ultrasound in ultra experiments, or in cavitation experiments, or in ion acoustic standing waves in a supernova experiment, those have got standing waves everywhere in that system, and so energy can accumulate and accumulate and accumulate, and matter can accumulate and accumulate and accumulate. That's the same as the Warren Cooley and Chuck Bennett pattern. When they initiate that original set of carbon buckyballs that are filled with deuterium, they then trigger that, produce the magnetohydrodynamic system in a water container that then confines that initiated magnetohydrodynamic system in the center by sound waves, producing that standing sound wave standing node in the middle, can keep providing it energy. Then it has self-healing water, which is fuel around it. So they solved so many problems with that pattern. I wish that pattern was available for us to review and not just the draft part of it. But here you can see what nature is doing. Look at this one here. There's a story there. These are ribbons of material. Now, where have we seen ribbons of material before? We have seen ribbons of material in the Bin-Juin Huang cavitation-based reactor. We saw one where it's like come out as a tornado, a second one where you can literally see it rolled up like a carpet roll, and another one where it hasn't unraveled itself enough to reveal it was a carpet roll. I think what you're seeing here is exactly the same kind of thing, a kind of carpet roll of carbon. Now, this is a fixed diameter because of the substructure. Now, I don't believe potentially that the original diameter was this big. I think it was probably much smaller inside the structure that was here. And as it became ordinary matter, it expanded out. So it's not only unraveling, it's going from a coherent matter wavelet into an actual ordinary matter as it's coming out, producing these ribbons. It's absolutely beautiful data. It's such an honor. It's such an honor to be able to have been a part of this.
It is. It's beautiful. And the reason why you're seeing them way out here, this is far from ground zero, is because it took time to mature. Yeah. And that's when they collapsed out there. And
look at this, for instance. Yeah. It's got a twist that comes up here, and this goes in. You can almost see a figure of 8 in here.
Folded over.
Yeah. This kind of experiment, thank you, Dr. Matsumoto. It will reveal so much of the process that's going on, and it's going to be easy to repeat evidence. So remember, we were using lead wire, potassium hydroxide, deionized water, and copper, and 120 volts at 50 hertz AC, and that's it. Look at this. It's a real ribbon. It's a real fiber coming out of here. Look at this. You can see where it's splatted, and you can see it's literally, it's got the hard part of the ribbon here and a little notch there, the hard part of the ribbon and a little notch here. You kind of get to understand what's going on. Was this the thing that landed here? Yeah. Maybe. Looks like it might have been. Yeah. Look at this one. Look at that. It's like a twisted ribbon, but there's the hole. Did it spew out? Did it just fart it out? And it just, the material went like this. It just went like that as it's trying to unwind. And what you see actually, and when you look at the high resolution imagery, and we're going to look at that in a minute, is that the shape of the outside of the ball is different. And it's different because now we are looking at lead. We're not looking at, for instance, in the case of Bin-Juin Huangs, we're not looking at copper with phosphorus in there. We're looking at, now look at this one here. Look at this. clearly coming out of the bottom there, came in at this angle and kind of died and fell apart. Absolutely stunning. There's just so much data. It's so data rich, and you're going to have all of it to look at. Now, there are a couple of balls on here, I have to say. They do look a bit like they're iron-rich crenellated spheres. Unfortunately, we didn't have a chance to verify that. And I think there's at least two. And maybe you can find out when you have a look at the data yourself. Anyway, right now, I'm going to go and look at some of the high-resolution imagery. And I'll hand you over to Paul for his thoughts.
So, Bob, will we be able to mark the coordinates on the image when we're using it in the software and then say, okay, could we have a closer look at that when you do the scan? I guess not. We'd have to rescan it, right?
Yeah, so the way this works, you do a map like this when it's in the SEM. And what I planned to do was to leave it in the SEM, but I didn't realize it was being taken home that same day. And I would have come in, because you don't want to contaminate it.
Right.
And I also wanted to see if any of these things evolved over a number of days, like Matsumoto observed.
Right.
So I wanted to leave it in there, scan it as immediately it was dry, and then do it again a couple of days later. So there's so much more that can be done, but already we're getting to learn so much out of this one experiment immediately. So it's absolutely not a dud. It's a fantastic success in my opinion. And like I say, I can't iterate how much it was a pleasure to do this with the Matsumoto family in the room.
Yeah, I think when I imagine this reaction happening is that because all these carbon bits are on the outskirts of town, basically right at ground zero, if you think about it, that matter would have been splashed. It would have been airborne or going through the solution. So those balls had time to mature and to cook as the condensed matter's rolling around in there. And that's when they landed. So they would have been moving above the surface of the copper and then actually splashed down out there. And when they came down, then the sphere cracked open or just couldn't take it anymore and blew out right on the surface and unrolled those sheets of obviously like graphene.
Or something, yeah. It's difficult to know really, precisely. I mean, these are. I think that they're almost what I would say they are crystals, but I think they were spinning around in a vortex in one side and the other side, and they unwound and they also expanded as they unwound.
Because they're so square. That's
yes.
So many of them are just a perfectly rolled out piece of carpet. So I picture it as like a sheet of graphene, carbon nanotubes, and there are multiple layers because the carbon will do that.
Now, of course, there is this question: is this all carbon that was either in the lead or all carbon that was in the copper? I doubt it's in the copper because I think most of these are formed in the lead. Right. It could be that there is lead carbon in the lead contamination. Regardless, what we know for certain is when we look at this, carbon was caught into these lead balls and it is coming out of these lead balls, right? That is 100% certain. And, you know, there are signatures that are showing helicity.
Yeah.
Okay? So it's just a behavior. Okay, so I am struggling to find these things, so I will leave you with there.
They're definitely traveling with the lead. I wonder if it could be, is there any possibility that it could have been around the outer layer of the lead traveling to the...
Well, there will always be some carbon on the outside of these structures because it goes through this core and goes round the outside. But inside the lead ball is where you tend to get a lot of the carbon persisting inside the sphere. And the lead tends to be captured on the outside. Now, I want to revisit the notion of coherent matter waves because that is, in my view, what all of this is. Because when we look at the high resolution images, which I do believe I'm going to find soon, too many things.
The other thing we see a lot of in there is the crystalline forms, and lead will crystallize like that. in a lot of cases.
Yeah.
And some of them really have really nice crystal patterns in them.
Okay, so I'm going to look now at a couple of these structures here at higher resolution here. So here was one of the lead balls which I showed it coming out clearly. These are quite thick structures, but they're very smooth.
Yeah.
You know, so how can you get carbon spewing out of
flowing.
something
Yeah.
and leave it with nice curves and stuff? Look at all the way up to here, the first interaction area. Here, look at this one.
It's
really
just square.
square.
Just crazy.
Clearly, in my view, it hit here, and that caused a rupturing. The material came out. Now, did the material come out instantaneously at this size, or did it come out as coherent matter and then crystallize in this form? I kind of suspect it was the latter. And I suspect the fuzziness you see is the remaining coherent matter just like flowing out and becoming carbon.
Yeah.
Look at this.
Layers. Yeah.
Look at this.
There's two of them.
This is 2. Now
Spewed
look at the
together.
previous one.
Yeah.
Look at this. This is 50 microns. So this is 25 microns. This is about a 20 micron ball. Okay, and one band here is about 15 microns fully expanded. This one here, what have we got? 50 microns, 25 microns again. This ball is about a 25 micron. So very classic 20 micron exotic vacuum object boundary layer, a boundary layer. That's not the internal structures, okay? But when we get down to this one, which appears to be a pair, one is very, very clearly much bigger. This is around about 50 microns, and the things that are spewing out of it are not the same that we see typically. And in fact, this is quite a rare one. If we go into this image here, you'll see actually it's in the top right hand corner, and it's this blob up here. It's a really rather large one, and its expelled material is very different from the typical ones.
Yeah.
Okay, so this is a little bit more action going on in here. Okay, and this is where I'm going to focus on a couple of points.
Look at that.
These, firstly, we have these crystals out here.
There
Okay.
they are.
Now these crystals come in a series of quantized sizes, like this size, and this size. And they also seem to have a bit of carbon fuzziness around them.
Yeah.
But they seem to be very pure. Now, I've looked at other SEM images, and they say that these are lead iodide. Now, there's no iodine in there, and when I looked at this, and you'll see it in a minute when I show the SEM analysis, this actually is not iodine, okay? It is predominantly a pure lead crystal, okay? With possibly some contamination viewed, because it's extremely thin. So if we can assume that these are lead, and take it from me, they are lead, and you're going to see that in the analysis. What we're seeing here is a load of small ones coming out of the center, getting bigger, and being big on the outside. Okay? And then there is this wavy pattern that you see around the outside. Okay, it's wavy, wavy, wavy. This is exactly what we saw on the last presentation I did, where I showed you the Vega experiment of Jan Rack in his lab, where we saw this kind of like wavy thing around the outside, and I compared it to a cactus growing, where it grows from the center and it grows out and it throws out particles at phi ratio, and it ends up with the maximum packing density, and it flows out. And what I imagine these things are doing, whatever the electrodynamics are inside, it sucks things in through a cone and through a cone and a counter cone inside, okay? And whatever happens, the bit that goes through the middle ends up by throwing things out at phi, and then phi, and then phi, and then phi, okay? And as that does, it wraps the coherent matter around the outside of the apple-like structure, and it comes round and goes back in up the arse, okay? So it goes round and in. But it's part of how the structure works. And if you could imagine that coherent matter is then rolling towards the camera here, it's coherent matter, and it's able to interact with normal material in a very different way to what a drill bit would. It's actually doing it in a Ken Shoulders says these structures, they have a binding energy that's higher than any ordinary matter, and so it allows for novel nuclear interactions. But it also allows for, if you remember what I shared recently, it allows for interactions that are not thermal. That is to say, the electrons or the bonds in even refractory materials and metals, they kind of give up holding together in the ordinary way. And so what I see is, when I look at this now, and I think you'll come to terms with this in due course, is that what you're looking at here, just like you were looking at in Bin Chuan Huang's reactor, is this is the frozen coherent matter wave and wavelets that are collapsed. And what happens if a thing collides into the surface and the coherent matter wave is sufficiently disrupted by the interaction with ordinary matter, a piece of that wavelet is thrown out, and that coherent matter wavelet then collapses as an actual pure crystal. So these are not a pure crystal that was come from here and flew over here and decided to land here. This was a coherent matter wavelet that was broken off, came here and then settled here. Now, why am I really interested in saying that? John Hutchison, the Philadelphia experiment, and Leonid Roitsky's testimony from his experience at Chernobyl reactor. What am I saying? What am I saying? I am saying this, and I'm categorically saying this. Of course, it's my first reading. That what is going on here allows for what we see here. What are we seeing here? What are we seeing here? What are we seeing here? But more importantly, what are we seeing?
Oh, that's a nice one.
Where is it? What are we seeing here?
Embedded in the, yeah.
What are we seeing here? And what are we seeing here and here? What do we think we're seeing? What do you think we're seeing there, guys? Refraction? That's a good guess, Power and Pep. Not a bad guess. Yin knows what I think. I'm going to ask Paul, what do you think we're seeing there?
Well, the ones that are sort of half embedded into the material, I think they're kind of sort of half embedded into the material.
Yes, Paul. They are half embedded into the material. What I think you're seeing on the screen there, right there, is a coherent matter wave that was in a neutral state, carried in an EVO, and it disrupted half the way in, or even in the case of these semi-transparent ones, because the electron beam can look through and see elements underneath. It is reappearing into our space-time, either into or fully underneath, or partially in and out of the surface. When S.V. Adamenko created his Proton 21 lab, he was creating elements, and they flew out from the pure copper target, and they interacted with the surface. And what he found by using an ion beam, and you can go and look at this Controlled Nuclear Synthesis book from 2006-7, he found that as he dug down, the elements might get less and less and less. That's one thing.
Right.
I have a sample from John Hutchison, and in the case of John Hutchison's sample, it was in a metal box and it was brass, and the brass had partially gone through the metal to the outside, but in the actual steel on the cut line, inside the steel, there was little islands of the brass, like in the steel. Not smeared in the cut line, but actually an island in the steel. Now remember what Leonid Roitsky said. He joined the field of cold transmutation of nuclei and ball lightning. Why? Because when they were going under the Chernobyl reactor, they saw little balls of light going around. When they were observing what had happened, they had large chunks of equipment, metal equipment, that were supposed to be in one part of the reactor, and it appeared in another part of the reactor. They also had steel girders where you kind of like had an I-beam, and the I-beam had intersected into another I-beam without deforming it. Right? Not welding, not bent. This beam was in this beam, split like that. Right? But the most interesting thing is that in an RBMK reactor, this is the type of reactor that Chernobyl was, they had this huge, I think 2,000 ton, very heavy roof, and inside there they had these graphite blocks, and they're about 40-50 centimeters long and about so big. They're ultra pure graphite, and the reason they're ultra pure is because they are the moderator blocks for the RBMK reactor. That is to say, they slow down the neutrons so they can take part in the reaction. These blocks are actually quite brittle. You can like break them in your hand like that. Or somehow these blocks had come from inside the reactor through that 2,000 ton roof up into the sky and landed quite a distance away from the reactor, and they were perfectly intact. That is one thing. But the other thing is this, which is really interesting, is that he developed a 2-ton gamma camera. Now, gamma is stupidly difficult to image, so he actually created this quantum lens, which looked like a three-legged, Norse symbol, okay, and it was able to use the refraction of the gamma rays to actually be able to image. And they flew this thing using the world's largest helicopter 400 meters over the reactor, and they could not find any sign of the uranium core. So they already knew from digging underneath it there was no core, there was no China syndrome melting down. They also found that they couldn't find the core. But what they found in these unbroken, undamaged on the face of them, graphite blocks was islands all the way through of not only uranium but all of the standard elements you would see out of what I call now coherent energy transformations, smeared through this. Not only that, his ultimate statement that he gave, because he was talking about this because of some of the lies going about Chernobyl and some of the kind of like fantasy stories going out that were getting a lot of traction, but mostly because his colleagues that he worked as a leading scientist trying to work out what happened in Chernobyl, they were all starting to die off. And he had to get it on the record what he saw that absolutely was not explainable by mainstream physics. And that is, and this is the phrase he used, the smearing of the Chernobyl reactor 4 through the entire structure of the Chernobyl reactor. That is to say, it's in the concrete, it's in the RBMK graphite blocks, it's in the steel girders, it's literally everywhere. The mass of that core of the reactor is blended into the structure. I say again, if you go and see my Cosmic Summit presentation, where I was shocked actually, where I read the account of what happened in there, where the Tesla apparently created 4 conical Tesla coils, special coils, because that's what you would actually need. When you arrange them in the size of that hull below the sea line, you end up with a structure that literally produces an oblate spheroid, which is the description, that is exactly the right distance from the side of the hull, extends out 100 feet. Exactly correct. And as you know, you can the claims about that was people were found to be blended into the ship, smeared into the ship. That is to say, you could imagine a scenario where the ship itself, the metal in the ship in places became coherent matter. It was kind of like not presenting charge. It was not presenting ordinary mass and inertia. And what happened was the people moved themselves into where the former parts of the ship were, and they when the field collapsed, they found themselves half embedded into the steel. And yes, you are right, Mick. Beam me up, Scotty. This is how you would teleport. You definitely wouldn't want to teleport into a lump of metal. Let's put it like that. But teleporting from a point in breathable air to another point in breathable air, that would be, very good. Now, one other last point I'd say is there is a phenomena with a particular technology which we have verified, and another phenomena which we've also shown. And that is to say, we have shown that HHO, specifically in the form, although we replicated it in Canada with David Boutlier, in the form of a Marsa gas, can weld dissimilar metals. And one of the famous examples is welding aluminium to steel, right? This shouldn't happen. However, we have shown that coherent matter wave structures, these magnetohydrodynamic structures that produce this coherent matter wave, occur when you use HHO gas. So if you're creating coherent matter wave structures, and we know that some of them structures can be, let's say, iron, and can be, let's say, aluminium, if you're creating that on a boundary layer, you can imagine something where an aluminium crystal, let's say this is an aluminium crystal, re-emerges out of its coherent state, half embedded into iron. So while these things do not typically mix, and you can't typically weld them together, what you end up with is a load of keys locked into the iron metal of aluminium, so you can weld them. For me, this particular set of images that we have got from this few-second experiment from Dr. Takaaki Matsumoto's mind, replicated in the last few days at the Advanced Energy Systems, explains some of the most unexplainable, non-mainstream physics describable technologies that have ever been observed in science. And you can do it for pennies. How does that make you feel? So I'm just going to run through a couple more images we have here, and then I'll run through the analysis. Again, look at this one. It's come out. It's a real wound up blob. Look at the curves on the end of this.
Yeah.
Look at that.
It folded.
And this band, it's literally like a ribbon, but it has these beautiful curves at the end. And clearly it came out of whatever this was and it died. And this one here is an overview of an area. And you can see, look at this area here. We looked at that close before. Again, over here, a little ribbon coming out. So I'm going to go through a couple of the analysis so you can see what was observed. And particularly, I think it's important that we see the elements that were observed in this. So here is the whole experiment analysis. And I will share this data, of course. So you can see here the two of the strike marks. We only got to look at this. And we did another session where we saw that the copper was pretty pure. So we're moving around this structure, having a quick look. We then do a map. This is the actual creation of the map. And then we look around as we've been doing today. We see these nice structures. And this one here, and so on. But then we go and map this particular one here in a little while. We will. Now look at this. I haven't got images of this other than here, but you can see this sloshing. This is the kind of sloshing that was described by Ken Shoulders right here going on. And these lovely wave-like structures. And also, we've got these pits, hexagonal pits cut into the copper. And you can imagine an Evo came in here and then came back out of it and left behind this section of copper removed. All the way round, you've got these stress fractures and these hexagonal pits. There we go, there we go, there we go. All right. So you can actually go and look at that on the sample here. Now, I'm going to image this. This is me capturing that image, and then I'm going to look at the elements there. And first off, I think we look at, where is it? Adding measurement. Where's the measurement gone? Okay, so I think there's one sample. I can't see where I've done it. Where have I done it? It's a map. Oh, I'm doing a map area here. Okay, so this map comes out. Now, this is where I said to Paul, are you sure you had potassium hydroxide?
Right.
Because potassium is in 36 units here in weight concentration. Actually, I'll go over to atomic concentration. Do I actually look at atomic concentration? There, yeah, go there. So potassium is 13 units, carbon is 10, and oxygen is 58. So I question whether there isn't some potassium carbonate in here. But we know the other structures are producing carbon. We know we had potassium hydroxide, and there's obviously water in there. So potassium carbonate is a chemical compound that could be formed. But what we do find in there is when it's showing itself here in the map here, is there is calcium and there is silicon. There's silicon in there. Now, we didn't have silicon in there.
No.
And look at this, we've got some iron. 1.81% by mass concentration.
Yes, very interesting.
Now, where is that iron coming from? And it's in here. So a lot more study needs to be done, but we're starting to see the kind of products that you normally get out of these systems. Calcium, iron, silicon, aluminium, and nitrogen, but of course nitrogen's in the air, so you can't really think about that too much. We then look at this little structure here, the little crystal there, and you can see that by weight it's 67.9% lead, and then it's got some potassium and oxygen in there, and that's pretty much it. And I think, and then we find this structure, and it's really rather lovely, but unfortunately I don't get a chance to image it. But clearly this ball spat out this, and then it went over here. We can see this is 2 micron. Okay, so we're actually looking at this is only a 4 micron across structure. So this, in my view, would be a smaller substructure of the bigger ones. Okay, but it's got a very different kind of structure that it's laid down on here. And it's like a foamed carbon type form. And it looks like it's domed. And in fact, we find out it's domed later because we go in and the guy that's running the show for the where is it? We find it later in a second. He turns on Chemisem. This is me imaging those. What did I image there? Oh, I'm looking at the material emitted from the back of this, and it's saying, well, it's very close to the lead. It's seeing the copper. I don't know, because the imaging is not actually working properly at this time because I shut down the map. But here we go and find this particle again, and he turns on a new technology in the scanning electron microscope called Chemisem. And I put the carbon on there, and you can see that basically this is carbon, but you don't see the backside. And what does that mean? It means that the electron beam is coming from over here, and what you're seeing is a very large dome. So we already established this is in the few microns across scale. This is a very small structure, and what we're seeing here is a dome. And I think what happened is this came in and kind of like got very close to the surface and did like an air burst, spat out the material, and you can see that it's kind of like all fanning out from this central point here. It launched itself a bit up into the air and then crashed down and died here. So that is the kind of data that we got out of this one experiment. But for me, very simply, in review, this data shows a system that is able to, at the very least, capture carbon, transport it, and deposit it elsewhere. At the very least. If further experiments are done and we verify using very pure materials that this is actually synthesizing the carbon, that's very, very interesting. But right at the end of this video, we see something that I wasn't able to capture because the guy came in and shut it off. It was like that. And it's a dead shame because right here in the center of the frame, you can see a roll. And this is almost exactly equivalent to the roll that we observed coming out of a Binwen Huang structure. So I think it's a very similar thing going on. Again, we have another one of these structures with the foamed kind of carbon.
Yeah.
So it's at various scales. So conclusion here is it's a simple experiment. It produces extraordinary results. And the data that you see from these kind of images here, and by the way, whilst I am here, I will show you this before we close out. what you're seeing in these is these little structures seem to chew into the copper. You see it kind of everywhere, and you'll be able to study it yourself in these images. So this one has made this channel here. It's this dual-sided channel. Again, this one here, there's kind of these scratch marks going along. All over, and these are very, very small things. But also, from these little platelets of pure copper, pure lead, you see these little splatters of the dark carbon. Again, in this area, you've got some splatters over here of the carbon, and then it's got this channel, and these little particles seem to have eaten out some of the copper. You're going to enjoy studying these, I think, and I would hope, all over there. So, this for me here, not this one. This one is the most important of the day, because we see silicon, aluminium, and iron coming out of a larger structure. A larger structure may be one where you can imagine that the internal structures have got very, very strong. It does show, in my view, the wavy coherent matter wave collapse structure, which in this case, because it's predominantly lead, presents itself like this, flowing in from the core and out through the outside. And this would be the north pole, and the south pole where the vortex is coming in through the bottom. And when the overall electrodynamics collapse, it spews it out of the bottom. And then you have these little things that are sometimes partially under the surface, partially penetrating the surface, sometimes directly on the surface, or as you can see over here, half in and half out of the surface. And this little bit of data here, in my view, explains HHO fusing dissimilar metals. The observations of metal being partially inside other metal, that is to say synthesized metal in other metal, in this case typically copper, in the Sviatomenko system. Metal appearing inside metal inside the Hutchison effect. Metals intersecting with other pieces of metal, and metal and other elements smeared through the body of the Chernobyl reactor, as observed empirically by the Russian mainstream scientists, which they could not explain. And lastly, the ability of HHO, or Amasa gas, to allow welding between dissimilar metals. And on the little bit crazy, the old Philadelphia experiment. I think you can create the Hutchison effect and the Philadelphia experiment for pennies on the dollar. So if anyone's got any questions, either in the room or out there in YouTube's land, I will try and field them now.
Yeah.
Any questions?
Spectacular. Just one comment. You know, if you scroll over to one of those square ones, I was thinking about it now, how a lot of them are broken up in the center.
Here?
I guess, well, in the other image where they're like the rolls. Yeah. You see how they're pulled apart. It's almost like the one just to the right of it in the bottom corner, there was two pieces, and we saw a lot of those that are separated in the middle. It almost looks like it was sort of an attached structure, and then it got stretched apart as if...
Oh, some of them are clearly carrying a tail.
Yeah.
And I think the tail might be a tornado.
Right.
And so it does look, when you see some of these breaking up, let me see if I do this right. We go there, and we go here. Where are we? This one, I think, was already behind this.
Right.
And what it might be is...
The part got stuck and it pulled it apart.
Well, I think what might happen is, as the confinement breaks down, the structures start to launch themselves, because the material is now ejected out from the center.
Yeah.
And then it's launched itself, and that bit that's come out is already coming out of coherence, and then it collides here, and more of it comes out as it comes to a rest.
Right. Yeah.
So I think when it's actually properly formed, the material is all trapped inside the ball,
yeah,
and then starts to decohere, starts to eject, that launches it off in a direction,
Right.
collides in, more comes out, dies, and the rest of the payload gets spread out.
Because many of them are split like that.
Yeah, plenty of them are split like that. And again, with a deep study of this, all of these mysteries are going to come out. This one's like fully on
Yeah.
broke out.
Yeah.
I mean, this is just spectacular for me. And like some of them get a chance to like form a crystal, like down in the bottom corner here. This one's formed like a. You can imagine this is a diamond crystal, but and also the substructures.
Yeah.
These little things, they're doing the same thing.
Yeah. And the tracks they're leaving.
Yeah,
as
they're
well.
leaving tracks, and yeah, I mean it's just amazing. It's just totally amazing. Yeah, but this one has got so many things to think about going on. So, any questions out there in YouTube land? What is that connecting them? Connecting what? Have you thought about scanning these to an STL with a 3D scanner? That would help in this research. Actually, okay, so that's an interesting question. What you can do on that SEM, when you have more time with it, is you can actually move the SEM in such a way that it can take a 3D relief map. And so you will be able to understand the 3D form of some of these, at least it's kind of like 2.5D. It creates a depth map, and then that will project a mesh. So you'll be able to understand more about what this shape is and the relationship to these and the relative distances, and you'll be able to measure how high above the surface this particle is. Okay. Can you explain a little more what it means for an exotic vacuum object to carry a standing wave? Yes, certainly. So an electron effectively is a centripetal de Broglie wave. So it's the matter wave that is held at a particular orbit around a central point. And that is according... And in fact, I learned this phrase from the text of Warren Chuck Bennett and the other author of that 1995 patent. They say basically what we're talking about in this patent is centripetal de Broglie waves, which are the definition of matter waves. That is to say, a wave that then folds in on itself. And so an electron at a particular orbit would be this. Within its space-time bubble, with all of the attractions and so on, it would fit. And so the end of its wave would be the start of the next cycle round. And so it stands there. And depending on the actual space-time in there, then it would actually move in and out. Okay, and the space-time, in my understanding, is distorted by the actual size of a nucleus. So the way that an electron could orbit at a particular orbit is affected by the size of the nucleus, because the nucleus itself is locally distorting space-time. So that gives your orbital levels. When you get coherent matter waves, you've got to imagine that these things are located on top of each other and on top of each other in the same way that a laser's photon is overlaid onto another laser's photon wave. So you effectively have more energy because you've got the same photon frequency in phase, traveling on the same photon frequency in phase over and over and over again. So you've got to think that that is just a photon, but matter is kind of like a trapped photon. And essentially it's all the same thing, it's all trapped light. So it's kind of that what's going on, and then you've got more of that going around in something that is... it's basically in our space-time, but it's got its own, it's creating its own local space-time. And so I think that's why it does some very interesting things when it's traveling through ordinary matter, because it's forcing that ordinary matter that it's traveling through to experience the space-time that is, by that I mean, let's say we change the dielectric constant, the physical vacuum, the speed of light and time changes within that space. And so you're changing time, and you're changing also the behavior of any electrons that can exist within that bubble. So as it's going through, it's changing. As any electron that happens to be either sucked in or be forced into the event horizon, it doesn't behave like the ordinary electron does in our ordinary vacuum energy state. It behaves like something different, and it probably turns to mush, as we observe. How thick was the copper sheet? How thick was the copper sheet?
Yeah, maybe about
200 micron or?
Yeah, 0.2, 0.3
Yeah.
of a millimeter, yeah.
Something like that. I can measure that. We have it. I just don't have it with me today. But we can get that for you. Thank you for that question. Question: how can Musk possibly not be aware of this tech and the history? Musk is a brilliant commercial person, and sometimes you don't need to have the latest, greatest to make a lot of money, and he's proved it. Okay, so that was there. Is the crystal changing over time? You mean, is it a time crystal? I think it might be changing over time. Certainly, Matsumoto observed solitons that were bound to iron and only to iron in his experiments of the metals that he used, and then it changed over a period of 2 days, leaving a deposit in which he found synthesized elements. AthenaMax says he's answered the question for you because he's a technocrat. So thank you for that comment. And Crypto Builders Keep comment is he's probably well aware. Okay, so in the context of the Philadelphia experiment, can this hypothesis prove relevant to MH370 asking for a friend? I certainly think that things that can make things disappear are useful to something that is claiming to make something disappear. Is there a video on the MFMP YouTube channel that discusses your view of the event? Yes, it's called My Movie XX Years On. If I were to reproduce this, how could I get images to see if it worked? I assume such microscope is out of my price range. Well, certainly that might be, but I have a microscope called a Narugu, and it's a 400 times microscope. And I don't know whether it's still available, but you might be able to get one as X stock. And it was about $70. And I coupled that with a Samsung S7, Galaxy S7, which is around about, 2012, 2014. Anyway, it has a beautiful Sony 12 megapixel sensor in there with large pixel elements in there, and it has a single light, single sensor. Absolutely no AI. You don't want any AI because you don't want it thinking it's trying to make something that isn't there. You want it to give you exactly what is there. And this will give you a 400 times magnification, and you're going to see a lot of these structures with that. And in fact, when I've done a proper SEM on these, I will then run it through the Narugu, which gives you wonderful color imagery, and you can actually capture that on 4K. And then in certain software, you can buy that allow photo stacking, but also in Photoshop as well. You can take several frames from an image where you take the Narugu and the S7, you move it slightly up and down, and it gets different focal planes. You can then focal stack that, and you can also create higher resolution images out of that. So there's a good way to do that. Okay. Okay, so you want? Oh, I'm talking to you as talking, and I've got nodding and yawning behind me. Yes. I think I'm wearing out some people in here, but okay. So yeah, hopefully that answers your question there. Can you explain a little more what it means for an Evo to carry a standing wave? I've answered that one. Have you thought about scanning these? Yes, I have. Says okay, all right, right. Okay, so I think I'm going to wrap up here. I will share the video of the SEM session so that you can see the analysis. Unfortunately, again, when you do when you kill a session when it is doing a how should we put it, a large area scan, it causes an overlay on the software that means you can't actually save your files which you've captured the SEM, but it's in the video recording. In part, that's why I do the video recording. Before I close out, I just want to show you this part, which you'll be able to see yourself. but it kind of tells you a little bit of what's going on this piece here. This is actually a very large chunk, which we can see here. We know it's a large chunk because we already know that this here, if I actually go and measure this structure, which we imaged better, but this is in the deep zoom image. This is over 50 microns across. I would say that the main core structure is a classic 50 micron structure. Okay, so if we get that round about the center. Now, if we go down to this one down here, this one's kind of like folded itself into the surface, but we can see one structure out here and one structure out here. And this is clearly twisted one way. Mm-hmm. So, as I say, you guys are going to be able to, if you wish, you're going to be able to find out things, and this is like 60 microns. This is even bigger than this structure out here. But I suspect what this is this is a 50 micron structure because it's a quantization level. And I can see a kind of fissure around there, and it's basically crashed into the surface and spread itself out a little bit like butter on a frying pan. Yeah. So I think that's kind of what's happened there. But you're going to be able to tell me things about this by studying this data. Mm-hmm. And isn't that a great thing? So, in summary, this was Ode intersection. And I think by understanding how lightning can manipulate matter in extraordinary ways, we have found that potentially this data here, and more specifically, very specific images that we've captured with this data, show a phenomenal process that can occur where matter can lose its charge and allow itself to move into other matter and rematerialize. This, therefore, is showing that matter can be teleported. And you don't want to be teleported in something that is incompatible with your biology, like a lump of metal or a lump of rock. That would be bad. And yeah, that's quite exciting. So with that, I'll say buenas noches, dobronoc, good night, and I'll hand it over to my colleagues in the room, including Yin, who can also say good night.
Good night.
And thank you, Bob.
Dobro's nuts. Yes, thank you.
Yen is just right here.
She really is. Bye-bye now.
Good night, Bob's World.
Bye-bye. Okay, cool.
Yeah.